In this tutorial we look at an example for the integral test. Let us consider the series taken over the sequence n times e to the minus n square for n running from 1 to infinity. We need to observe that we can link the underlying sequence of the given series to the following function where f of x equals x times e to the minus x square for x greater or equal to 1. Here the idea is that we take our sequence, which is defined for all integers n greater or equal to 1, and make it into a function, which is defined for all real numbers x greater or equal to 1. We do so by simply replacing the n's by x's. Then clearly f of n coincides with the nth element in our sequence, that is n times e to the minus n square for all integers n greater or equal to 1. Furthermore, f is continuous since it is the product of two continuous functions. F is also positive as x is greater or equal to 1 and the exponential function is always positive. Finally, f is decreasing. In order to show this fact, we need to do some analysis. For this purpose, we determine the derivative of the function f. Since f is a product, we need to apply the product rule to find f dash. That means we first differentiate x and obtain 1 times the second factor e to the minus x square plus x times the derivative of the second factor, which turns out to be minus 2x times e to the minus x square. Overall, we obtain e to the minus x square times 1 minus 2 times x square. As we already observed, the exponential function is always positive. Furthermore, since x is greater or equal to 1, we can be sure that 1 minus 2 times x square is strictly negative. Hence, the derivative of f is strictly negative, which means that f has a negative slope and is therefore decreasing. Overall, we have shown that f satisfies the conditions that are necessary to apply the integral test, which now states that our series converges if and only if the integral from 1 to infinity over the function x times e to the minus x square converges. So let us calculate this integral. First, we get the following. In order to solve this integral, we need to perform a substitution. For that purpose, we set u equal to minus x square. Then du equals minus 2x dx. Furthermore, our limits 1 and t change to minus 1 and minus t square. Now we can transform our integral. First, we get our new limits. Next, we want to replace e to the minus x square, and because of our chosen substitution, we get e to the u. It remains to replace x times dx, but from this equation, we derive that x times dx equals du divided by minus 2. Solving this integral is straightforward. In fact, the integrand remains unchanged and we end up with the following term. As is standard, we now fill in our limits minus t square and minus 1. As t tends to infinity, minus t square tends to minus infinity. That means e to the minus t square tends to 0. In particular, our limit simplifies to 1 divided by 2 times e. Overall, we have found that the integral has a finite answer, which means that the integral converges. Therefore, by the integral test, our series must converge.